Three presentations. I'll probably have a little word at the end. Did my presentation go on here, by the way? Did my presentation go on here?
Yeah.
Okay. Yeah, I'm just going to whip through it. Okay, so we've got three presentations as per the program, and I'm just going to have a little chat at the end about an idea. Okay, so what we have now is the first of our keynote speeches. We had the other night a public lecture by our keynote speaker, and she promises that this is actually a different talk.
It's not very different.
It's on the same subject. So, Monicagrady is a leading British space scientist, primarily known for work on meteorites. Since 2005, she's been Professor of Planetary and Space Science at the Open University. She's currently Head of Department of Physical Sciences. I'm going to pick a few things out of here. She's built an international reputation in meteoritics, publishing many papers on carbon and nitrogen isotope geochemistry from primitive meteorites, on Martian meteorites and interstellar components of meteorites. She gave the Royal Institution Christmas lectures in 2003 on the subject of Voyage in Space and Time. Asteroid 4731 was named Monicagrady in her honour. She's appointed Commander of the Order of the British Empire in 2012 for services to space sciences. She's the first UK scientist to be President of the International Meteoritical Society. The last thing it says here, her husband, Ian Wright, is also a meteoriticist. Some sort of meteor person, and we'll hear from him soon. But for now, please welcome Monica.
Hi, thanks Andrew, and thanks for the opportunity to come and talk at this conference. I must say the talks today have been absolutely fascinating in the breadth of information and the subject area covered. It's really great. Right, so me. Next. What have I got to do next? Where am I? Click on day one. Yeah. Oh, right, sorry. Hyperlink, silly me. Right, okay, thanks very much. Okay, so I'm going to talk a bit about the Rosetta mission. What I'm going to talk about has got nothing to do with drilling or mining at all. So I'm just talking about this space mission. My connection with the space mission is that I am one of the scientific advisors to one of the instrument teams that built one of the instruments on part of the mission. So I'm not, basically a major force in this mission, but I've worked quite a bit with the Rosetta scientists. So just to put this mission into context, it's been a long time in the making. This is the tour T-shirt, the back of the tour T-shirt. It was launched in 2004 and took 10 years to get to the cometary object that it's been examining, which is Comet 67P Churyumov-Gerasimenko, named after the two astronomers who observed it first in 1969. Now, as you all know, you can't just launch a mission from the Earth straight out into outer space to go as far away as Rosetta was going to be. And so the spacecraft took the scenic route after it was launched from Kourou in French Guiana, and it went 3 times around the Earth and once around Mars to pick up enough momentum so that it could be boosted out into the solar system beyond the asteroid belt, where it was going to rendezvous eventually with Rosetta, with the comet. So it did all these things. It flew by 2 asteroids, took pictures of asteroid stains, and did more work with asteroid Lutetia. And then following following the work that was done on asteroid Lutetia, when all the instruments were switched on the spacecraft, all the instruments were then switched off, and Rosetta went into hibernation for 2.5 years. It did that to sort of save fuel and to keep everything, nice and isolated. Everything woke up again in January 2014, almost 2 years ago now, and there was a lot of concern at the time because these instruments that had been put into hibernation in 2011 They had been built in sort of 1999, 2000 with technology that was current in sort of 1990, 1995. And so the idea of switching it off, putting it in a deep freeze under vacuum for 2.5 years, and then switching it on and hoping it was going to work first time was a bit sort of, there was a lot of tension at ESA when they went to switch it on. Unfortunately, it did switch on. I believe it didn't work first time. It had to be switched on and off a couple of times, but you know, you all have to do that with your plugs. So that was all right. It then spent 8 months or 7 and a bit months just gradually speeding up and moving until it caught up with the comet, and then it ran alongside the comet until November, and then we had the closest approach this year. So I'm going to talk just a very little bit about some of the instruments. I'm just going to mention a couple of the instruments and talk about some of the results that we've got from Rosetta. And then Ian's talk, which follows mine, is going to talk in greater depth about 2 of the other instruments. So Rosetta is made up of 2 parts. Sorry, the Rosetta mission is made up of 2 parts. There's the Rosetta spacecraft, the orbiter, and then there's the Philae lander. And there are innumerable, you can see 1, 2, 3, 4, 5, 6, 7, you know, sort of a dozen or so, dozen and a half instruments on the orbiter, most of which are concerned with measuring the dust, the gas, the the charged particles and the neutrals that are coming from the comet, as well as actually taking images of the comet. There are different cameras. There's cameras specifically for imaging, and then there's cameras for navigating. And then there are sort of radar, echoey sounding, radio instruments, spectrometers, the whole usual sort of stuff that you get on any orbiter that's going to go and orbit something that's giving off particles. On the Philae lander, we have 11 instruments. Again, there's cameras, spectrometers, but there are instruments which are going to measure the abundance and isotopic composition of the different elements that are in the ice and in the dust. There are also the other half of the echo sounding radio package concert. There are instruments to measure thermal conductivity, temperature, and so on. I nearly said pressure, but that's not really germane. Right, next one. Okay, so in my talk on Tuesday, I went through why this was called Rosetta and why it's called Philae. So, you know, since I've got the slides, I shall do it again. So the Rosetta stone is an object. It's about this size. It was dug out of the Nile at the time of the Napoleonic Wars. And there was a bit of aggro between the French archaeologists and the British archaeologists about who owned it, but you know, the British archaeologists obviously won because it's now in the British Museum. This Rosetta stone is famous because it has 3 languages on it. It has Greek, which archaeologists can read. It has Demotic script, which was the court language of the Egyptians, the scribes who were recording things. And it has Egyptian hieroglyphs, the cartouches. Now, at the time, in the 19th century, people couldn't understand these, had no idea what these cartouches meant. But this Rosetta stone, it became clear that the Greek and the Demotic were saying the same thing, and it was a declaration by one of the kings, Ptolemy V, who was reigned at about 200 BC. And because these 2 things were saying the same, they assumed, archaeologists at the time assumed that the cartouches were saying the same thing as well. And so that enabled translation of the Egyptian hieroglyphs, which opened people's eyes to what was going on in Egypt. The trade, the burial rites, the daily work that was going on, just everything about the ancient world, the cradle of civilization. So understanding, deciphering the Rosetta stone opened our eyes to humanity's origins. And so when you were looking for the name of a mission, to open humanity's eyes to not just humanity's historical and cultural origins, but the origin of life itself. That's why Rosetta was selected. Philae is an island in the Nile down here, and Philae was a centre of great worship for the ancient Egyptians, and it was the home of a huge temple to Isis, the mother of all the Egyptian gods. And at the gates of the Philae temple were two obelisks which also had Greek and the cartouches on. And they had different symbols, different cartouches. So the additional information that came from the obelisks at Philae illuminated what was learned from the Rosetta Stone. And so the idea is that by calling our land a Philae, we're going to illuminate the information that we got from the Rosetta mission. There was a third name, which is Agilkia, which is the name of the landing site where the Philae lander was scheduled to land. Agilkia is another island down here in the Nile, not far away from Philae. Once the Aswan Dam was built, which is here, the levels of the Nile changed and the Philae temple, the Philae island, started to flood. This is a UNESCO site of cultural heritage, so UNESCO moved the temple completely to Agilkia, which didn't flood. And so Agilkia was a safe haven for Philae. So the idea was that the Agilkia landing site would be a safe haven for the Philae lander. You know, it would have been wonderful if only it had worked. Okay, so we've got up to this time when the the comet, we got our first view of the comet. Up to then, we'd assumed it was some sort of approximately spherical object. This first image showed that it was approximately not a spherical object, but it was something that was more duck-shaped, like this. And as you can see, all the scientists who floated ducks in their bath were a bit sort of, well, how are we going to land something on this? Especially the engineers. A lot of time and effort had been putting into making an accurate shape model of the comet, so that its mass could be approximated. Because if you're going to drop something onto something else, you've got to know the gravitational attraction between the two bodies. So you've got to know the mass of the two bodies. So if you're assuming a density, you've got to know the volume to be able to get an approximation of the mass. Once it was seen that actually there are two lobes to this object, we didn't know at the time whether they were made of the same material, whether it was one thing that had bits broken off it, or whether it was two things that had coalesced. It was felt that the shape models were not accurate, therefore we did not have an accurate mass for the object, therefore we couldn't land anything on it. Now, if you're a bunch of engineers and you're telling people, no, you can't land on it, and those people have been waiting for 10 years to land something, you don't get very far. And there's a big, not quite a punch-up, but a polite exchange of views. And the engineers said, yes, actually, all right, we will land on it. So that was all well and good until a couple of months later, the engineers, you see, I can be terribly rude about engineers because I know there aren't any in the room. The engineers, we then got a better picture, and it's like, oh no, not only is it an odd shape, it's an even odder shape than we thought. It's got these really, really, dodgy looking bits on it. This is about, that bit there is about 4 kilometres across. So it's not a huge object. So you can see that these are quite significant features on it. Also, this is an image taken from Earth, from the VLT in Chile, and you can see here that Rosetta has developed its tail. It looks like, looks like how we think a comet looks. And you can't see that tail when you're up close, but it's there. There's huge amounts of gas and dust coming off the comet. So we've got this really odd-shaped thing, which is giving out, much more active than we'd anticipated, and also it's got, it's really, really rough. So again, the engineers, they kick up awkward and say, no, we can't land on it, and again, you know, polite exchange of views, and yeah, all right, we will land on it. So that all goes. Whoops, I'm just going to do it this way. All right, and this is just to show how big the comet is. This is ESA's very well crafted image showing the comet. It's about 4.1 kilometres across at the base. This is it projected on London, between the Tower of London and Big Ben. This is my less than perfect image showing Sydney. Well, didn't you recognise her? You know, you didn't recognise Sydney. This is a I don't know, some music centre or other. And actually, when I gave this lecture on Tuesday, you know, pardon my ignorance, I just said, oh, and this is a place called Redfern. I've no idea where it is. I've no idea whether it's important or not. And then several people afterwards came to me and said, you do realise Redfern is where the technology park is, and that's where the conference is going to be. It's like, so obviously very carefully selected and amazingly, Redfern is 4.1 kilometres away from the Opera House. So that's just to give you an idea. If you plonked the comet down on Sydney, you know, it's not big. I mean, you know, Sydney's a nice sized town, but I mean, I'm just sitting it there. I'm not you know, crashing it in at some enormous speed. I'm just sitting it there to give you an idea of how of its size. So we got to a stage in October when all systems seemed to be going for landing on the comet. ESA had several landing site selection workshops. Now, I've been to landing site selection workshops for Mars. And for Mars, you've got a beautiful planet, you've got enormous amounts of data and imagery and spectroscopy and all sorts of stuff where you can really do a lot of detailed investigation before you select a landing site. The first landing site selection for Philae took place when we had 1 pixel, right? The second landing site selection took place when the image was 5 pixels across. So you can see it was all a bit, you know, shades of grey, as it were. But by the time we got to this stage, you know, we've got a good idea of what everything looked like. And 10 sites were selected and then down-selected to landing site J, which was named Agilpia. And everything was all systems go then for landing on November the 12th. This was one of the last images we had of the Philae lander, which was released from the Rosetta spacecraft at 10 o'clock in the morning. It's going to take 7 hours to fall towards the surface of the comet. So there was a lot of time spent in Darmstadt where people were waiting for the signal to come through. The signal was going to be received by ESA's Deep Space Network, by the receiver at New Norcia in Western Australia. So, I mean, this is yet another example of the importance that Australia plays with space agencies. They're absolutely essential, you know, part of the Rosetta mission. At about 4 o'clock, we got the first image of the comet taken by the camera on Philae, and at this stage we got 45 minutes to wait for the signal, but we weren't actually going to get the signal until 3 minutes past 5 because that was because it took 20 minutes for the information to come back. So we saw that the thing landed. Oh, damn, really, already? Okay, well, it landed. Right, you can see its footprints, it landed. And then it bounced, all right? So this is a signal from ROMAP, the magnetometer. You can see it touched down, and then it touched down again, and then it touched down again. So it bounced, all right? So something went wrong. We already knew the thruster wasn't working on top, and then the harpoons, which were going to anchor Rosetta, didn't fire. But then it did. Eventually it came to land, but it didn't land in the right place. So we only had 60 or 70 hours of main battery to get most of the work done. Fortunately, we got a huge amount of data in that time. Some of the data came from the Ptolemy instrument, which Ian's going to talk about. So I'm going to very, very briefly skip through some of the information that we have had from the instruments on board Rosetta. We know how big it is, we know what its density is, very high porosity and very, very low albedo. It's black, it's really, really black. It reflects hardly anything at all. And that was a surprise. We weren't expecting it to be that black at all. You know, the old image of comets as being covered in ice, you know, was blown out of the window by the Giotto mission in 1985-86. But this is even blacker than we thought. And we're not certain whether it's because of cosmic radiation actually graphitizing some of the organics that are on the surface. Amazing imagery showing structures that you can see, and we can see from the way these structures dip on the two different lobes of the comet. This is what has made people realise that actually they're two separate boulders, big boulders that have come together. The high porosity is caused by the fact that the whole of these are sort of loose rubble piles with a very high void space in between. Okay, so here are some data then. This is from Vertis, which is on the Rosetta spacecraft, and this is reflectance spectroscopy, and this is showing how very, very black the surface is compared with some of the reflectance that you get from other substances. And the idea, you know, it's flattish anyway, and so it's not showing much structure in terms of how matte black the comet is. That was published in a special issue of Science at the beginning of last year. In the same issue, this paper by Katerina Altve from the Rosina instrument. And what this has done is this is looking at the deuterium-hydrogen ratio of the water that's come from the comet. Now, these data were acquired in August 2014, okay? And what Katerina and her team found was that the deuterium to hydrogen ratio of the comet is up here, which is within the range of other DH ratios of other comets that have been measured mainly by ground-based measurements. Here is the Earth, here is the protosolar nebula as represented by the Sun and the gas giants. And basically, if you mix this with that, well, you should be able to get the Earth, but you know, you're going to have to mix up a heck of a lot of it. So what the final inference of this paper was that the water on the Earth did not all come from this particular comet. Well, we never thought it did, but you can see that actually there are ways that you could mix the two reservoirs together. So basically what it means is we've got to look at a whole lot more comets. Now, much more recently, Ian's going to be talking about this work, but these are two papers that came out, well, this came out last week, this came out, I don't know, about a month ago. This one, the diurnal cycle of water ice on the comet. It's like, hey, they found ice on the comet. So what? This is a really, I think this is a really important paper, and it's one of the most interesting papers that I've read. It's in Nature from 24th of September. What they found is that when the sun shines on the comet, more water sublimes off it. And when the comet rotates round and it gets dark, there isn't so much water coming off. Now you might think, well, you know, so what? When the sun shines, the ice melts. But actually what happens is, once it's gone into dark, because there is a greater thermal lag of the rock rather than the ice, there is a thermal lag in the subsurface regions of the crusty bit of the comet. And what that actually means is that as the ice starts condensing down again, because it's gone dark, some of that ice in the pore spaces has a possibility to be there as water. And that water, because there's a lot of salts in the comet, could dissolve those salts. So you've got a possibility then of a brine which might remain liquid for just a little bit longer. And this is really, really interesting for the erosive processes on the comet. I think it's an absolutely fascinating paper. This paper as well, this was in Nature last week, and it was Katrina Altveg's team again have found, reporting that they found molecular oxygen coming from the comet. And this is really strange, you know, we don't expect that. They have postulated that this oxygen is primordial oxygen which has condensed down on grains when the protoplanetary disk first started, and it's been trapped within those grains ever since. Sounds a bit odd to me, but I don't know. They say they've ruled out every other possibility, including the fact that the water molecules could be broken down by radiation. But you know, so well, that's what they say. It's really interesting, anyway. So this comet is showing lots of surprises. Right, so this is my last slide. So Rosetta spacecraft, it's done its closest approach. It's moving away from the sun now. It's still very, very active. Philae is awake, but not talking to anybody. Or if it's talking, Rosetta isn't listening because Rosetta's too far away. It's gradually moving closer, but because the comet is so active, Rosetta can't get any closer to the comet's surface at the moment. There's too much dust coming off, and that really does mess up the star tracker for the navigation cameras. So, that's it.
Questions?
That's what Rosetta's doing. Any questions?
Just around with the landing of the philae, what do you think the reasons the bounce occurred, and the fact that it bounced and landed in a different spot? How did that negatively affect what you were measuring, and why did, as you said, it cut down the available battery time? So.
Right. Okay. We are trying to spin this in a positive way, and we're saying that we couldn't afford to put a rover on a comet, so actually we planned this for it to bounce and collect material in 3 different places. Yeah. No, there were 3 mechanisms that were going to hold the object in place, because you've got to remember it's a small object landing on a small object, and there's hardly any gravitational interaction. It's not going to stick there by gravity alone. So there was supposed to be a thruster to push it down, harpoons to fire to anchor it, and then like crampons on the 3 feet of the of philae. The thruster didn't work, the harpoons didn't fire, so that meant when it touched, it bounced off again. And then, you know, momentum brought it back down, and then it bounced again, smaller bounce, bounced again. And then instead of landing like that, in the middle of this sunlit Agalpia plain, it's landed like that on the side. It had got 2 batteries, a permanent battery with 60 or 70 hours power in it, and then a secondary battery which would be charged up by solar panels. But because it landed in the dark, those solar panels weren't collecting enough sunlight, so the solar panels didn't charge up. So that's why it went to sleep. But it's woken up now because as the comet got closer to the sun, there was more sunlight, and so the solar panels charged up. Okay. Any other questions?
Did any of the sampling that occurred on the surface of the asteroid confirm any of the remote sensings or the composition of it?
Yes. So Ian will talk about some of the molecules that they found on Ptolemy, I think. And yes, they found a lot of organics there, and carbon dioxide and water as well. But they haven't found graphite or graphitized carbon because the instrument wasn't working in the mode that it would need to be working in to detect that, because that would require a sample from the drill to go into the ovens, and that didn't happen because the drill wasn't pointing downwards.
One more?
Do the accelerometers give you an indication on the structure of the surface as it bounced? Is it layered or is it got crust?
Yes, I mean it wasn't just when it bounced, but also when the thermal conductivity, when the MUPUS instrument tried to push its way in to measure the thermal conductivity and the temperature, it found that it couldn't push its way into the surface. It was really, really hard, and they had to sort of hammer their way in, to the extent that at first they thought that they were hammering into one of the legs of Philae rather than the surface. But then they burst through. So the surface is really, really hard.
I think we're going to have to let the rest of your family participate in the proceedings. So thanks very much to our keynote speaker. Our next speaker is Professor Ian Wright. He's the principal investigator of the Ptolemy experiment, which is currently sitting on the surface of Comet 67P. He's a planetary scientist who spent his career studying the nature and distribution of light elements. He's designed instruments which have been used extensively for the study of meteorites, lunar samples, Martian rocks, cometary dust, etc. Spaceflight versions of the instruments have been sent to the surfaces of Mars on Beagle 2 and in the Comet on Rosetta. In the latter case, Ptolemy, a gas chromatograph mass spectrometer system on board Philae, has been successful in making measurements of cometary solids and dusts and volatile gases, as we're about to find out. Please welcome Ian.
Yes, and I'd like to start by extending my thank you to Andrew for inviting us here. It's been a fabulous day so far. Gone downhill a little bit now, but it's kind of, we're sort of down to earth in a way, metaphorically speaking now, I think. I mean, but I'd like to start by acknowledging my team. You're going to hear something about the journey and about how long it takes to do these things. And so I've worked with a core team of 5 or 6 people there. And there's more than 100 staff years of us working together on this project. Monica is one of the co-Is, and we have a co-I team. And necessarily, because these things take a long time, several people fall by the wayside during that period. You might think me and Monica would compare notes when we were providing talks back to back, but clearly not. So that's to illustrate the size of the Comet. And what I did was I thought, oh, well, no, I'll see if they did one for Sydney, you know. And so you put it in Google, and this is what you actually get. You get a picture of Warwick Holmes holding a model of the Comet there. But it illustrates, and that's Sydney Observatory there. But it illustrates a couple of things. First of all, if the comet was actually that size, the tail of a really active comet would extend from here to Brisbane. It gives you some idea about what you look at when you see a traditional picture of a comet. You see this massive great tail. These are the largest things you see in the largest structures you can see in the solar system. But the thing that's making it is relatively tiny. The other thing it says is something about the real comet is even darker than this model, and Monica's already said this, but this is what would actually look like normalised to the Earth, the Moon, and I think that's Enceladus. Can you see 67p? So it's not on there. Okay, so here it is, and gone through Photoshop a little bit. So I think you can get an impression just how black the surface is. And that's one of the fascinating things that we are trying to understand. And yes, again, Monica alluded to the fact that certainly we're old enough to have been brought up with this dirty snowball model. This is Fred Whipple here. And this is kind of how he envisaged comets. They were like a kind of ball of ice with a little bit of a coating of dust around the top of it. Well, clearly, comets are actually nothing like that in reality. So here's the iconic image, for me anyway, of 67p. And what I thought I'd do here is, because I thought there'd be more of this kind of stuff here, but so just to put it in the context of mining and so on, and what it might be worth. So the mass of the comet's 10 to 13 kilograms. It's got a dust to gas ratio of 4 to 1, which is actually very high. So from that you can calculate the amount of dust it contains. You can assume that dust is chondritic. And so it's gone off the edge there, but that would have 1 part per million platinum. So in other words, if you kind of had the whole comet, you would have 8,000 tons of platinum. And to put that into context, I looked up Bushveld, and it said they mine 5 million ounces per year. On earth is an ounce? But apparently that's what you use in the mining business. So that's about 140 tons of platinum per year. So that kind of gives an impression about what these kind of bodies might be kind of worth in actual terms. But I must admit, when I recast this talk, I'm going to do it on the basis of the value of the water it produces if you go into space and never think about bringing anything back, and then you use the water to produce liquid oxygen and fuel, because that's obviously much more relevant and interesting. Monica's already showed you a picture of the Philae lander. My instrument is on Philae. And what I'll start by talking about is the drill itself, because I think this is quite relevant to the conference. And what I would say is that's not my work. My instrument interfaces with the drill through the oven system. But this is work done by an Italian consortium of engineers and scientists, and it's run out of the Polytechnic of Milan. This is the principal investigator, Amalia Finzi, of that team. And all of the resources I'm going to show in this section could just come from their website. So you can see from there, this is the drill, this white box here. This thing here, so that's like about this high, and the drill can extend to about 56 centimeters beneath the bottom of the lander, and based on the fact that it's a few centimeters above the surface, it should technically be able to go 20-something centimeters into the surface of the comet. Here's just a few images. This isn't flight hardware, but if you kind of look through the side, you can see this carousel with these little ovens on them, and we'll see this in a little bit more detail here, I think. This is actually the flight spare model, which is actually in their laboratory. This is the electronics box. You can see here are the different sorts of ovens here, and this is a carousel in here, and these are 2 tapping stations. These are the stations that actually dock with the instruments themselves. There's another picture. This is a ground reference model. This is actually so it's not actually space hardware, but that's a space representative tapping station. So that thing's about like this big. That's the thing that's connecting the instrument with the oven, into which you hopefully have the sample to analyze. And here's a picture of what these ovens look like. There's 2 different sorts. This is a medium temperature oven. It actually has a square window on there so you can see into it. So you can't heat it to too high a temperature, but you can see what's inside it. And these are higher temperature ovens where you can, I was going to say bake the shit out of it, but whatever the technical term is. But you can't see into it. There is one of the ovens with actually packed full of sample, and you can. There's a little microscope that can see that, and it's just got infrared capability and so on. This just tells you something about the dimensions of those things. So the outer dimension of that oven is 5 millimeters. So the inner dimension, the thing that you're putting your sample into that you've now mined, is a couple of millimeters in diameter. This is just a page from my notebook. So this shows you we have 26 ovens on this carousel. So the drill can go down, it comes back up, the carousel can move around, and you can put the samples into one of these 26 ovens and move them around and dock them with the instrument. So here's their ground reference model in Italy, and they've been trying it out, drilling it into various kind of materials, and drilling engineers, I don't know what the miners do, but the spaceflight people always use this stuff. Well, they call it gas beton. I don't know how it translates. It's this stuff. It's like thermalite blocks, like breeze blocks. They love it. They seem to think it's a really useful analog of what you're going to get. And so here's some results of some of their test drillings into various materials, and you can see the drill itself. A couple of images here. So here's the drill going into a block of thermalite, and you can see it has this thing here. So what it does is it drills down into the sample, it then pulls back out a little bit, and then it can push that tube down independently to collect the sample, and that whole thing is brought back. And there's an engineering drawing of the drill bit itself. Well, you can see this tube here being deployed. Oops. And so that's how you get your sample, and that then is brought back and interfaces with the carousels. That's actually just a schematic of how that works. And I say all of these resources are on their website if anybody wants to see. So that is that's real mining going on in the field. And this was something they tweeted on, I think this was the second night of the campaign. And what you can see here, I mean, I don't know what all these things are, but this is the distance the drill travelled and back again. So they did an experiment where they sent their drill down, it came back, and everything worked perfectly. As an instrument team, they were extremely happy because that all worked fine. And here we are in the control room here. This is, I think it says 20 to midnight. I've no idea. We were awake for several days. Here's Amalia. They were extremely happy because this thing had worked. It had come back. It had docked with the ovens, and then the oven had rotated round to this instrument run by Fred Ghostman. He's the principal investigator of an instrument called COSAC. And he's talking here with Pierre Luigi, who's one of the younger members of the drilling team, and they're pretty much coming to the conclusion that, in actual fact, it didn't have a sample in it. So it's quite frustrating. And the reason for that is because of the way the land eventually ended up. Everything worked fine, the drill went down, but it couldn't reach the surface because the surface was too far away. And we've subsequently looked at the surface, and it's quite apparent if we rotate the lander, because the surface isn't flat, we will be able to reach it. So it's still a possibility that we can do this. So I'll very quickly go into our instrument, and the journey starts here in 1986 with the Giotto flyby of Halley. And one of the things I was doing at this point was building instruments in the lab, and I always had one eye on the fact that we would be analysing things like samples of comets that we were going to bring back. And the reason for that is that this was the talk on the street at the time. This was the study document that was produced between ESA and NASA. And you see, Rosetta was a comet nucleus sample return mission. So this thing was supposed to go there, take 10 years to get there, drill a sample, 3-metre long core incidentally, bring it back undisturbed, and we were going to analyse it in the lab and say, oh, that was great, I built some instruments to do that, everything was great. Clearly, you know, reality struck and that wasn't possible. So we kind of said, well, what would that, you know, could we take our instruments to the Comet instead? And I always like to show these things because they remind me that these are my back of the envelope drawings, and they're dated 14th of January 1993. So that's when I started work on thinking about how we could do this mining on a comet. Here's the same thing a year later, so you can see it really advanced in that year. But incidentally, I'm always intrigued that this is actually the instrument we built. We didn't have drawing packages in those days; they like hadn't been invented. And this is what we had to do. This is one of the instruments that we've got in the lab, still there today. It's a fantastic instrument. There's a lot of analyses of meteorites, moon rocks, and Martian samples, and so on. This is actually a Welshman for scale. Not very happy with this. You can see how, you know, these things are massive because we make them big, you know, because we don't have to worry about them in the lab. But if you want to take that to a comet, you've got to build it for 2.7 kilograms. So we said, well, it can't be that difficult, can it? And this is actually the mass spectrometer that we built, and that box there would actually sit on the palm of your hand. It weighs a total of 240 grams, and the actual mass spectrometer, that's a complete system, that's everything, including all the electronics and so on. The mass spec itself is that little bit there, and the electrodes of that weigh 15 grams. So clearly, if you put your mind to it, you can develop some really sophisticated instruments that can survive rocket launches and 10 years in space and all that other kind of stuff. Did you notice as well we were using nanotechnology in the source design? So this was something we were thinking about 15 years ago. Monica's already shown you the box there, the Ptolemy instrument that we built, and you can see a hand there for scale. You can see, you know, it's the size, we call it the size of a shoebox. This is the system diagram. It's very complicated. You're not really meant to see it because it was never intended for this sort of thing. But very quickly, we got the oven here. We got a section here where we can heat up gases, put them in there, do some chemical cleanup on them. We have three gas chromatography columns for doing the gas separations. This is the helium system. You saw 2 silver tanks there. That's the helium in them. That, incidentally, all this stuff worked perfectly and is still working now. We have a hydrogen system here for doing some other gas work, and then we ultimately have the mass spectrometer at the end. So it's a very, very sophisticated instrument. And it had to be like this because we didn't know what the place was going to be like that we were going to. So we had to, it had to have all kinds of capabilities, far beyond anything that we would actually need to use, we hoped. And we've used the instrument since we've landed in a couple of different ways, using a couple of different channels through it. But what I'll just talk very briefly about now is the sniffing mode that we did, which is basically we just looked at what was coming up through the exhaust pipe. Okay, so here's some more dates. This is 2001. This is the Philae lander, when it was 2 lumps of metal. And we were the first damned instrument to be integrated on it. Now, hey, youngsters, don't ever do this. Don't ever be the first instrument, because it means you have to be first. And this thing was right in the middle, and it was a bit of a pain. But there it is, sitting there, 2001. 2004, that was the rocket launch. Please go and see a rocket launch. It's absolutely fantastic. Principal investigators always have to go to rocket launches. It's just a chore of the job, really. There was the wake-up signal that Monica talked about, first image of the comet. Yes, problem with the shape, wasn't too happy about it. This was the day of the separation. This is the Philae looking back at Rosetta. You can see Rosetta here with the solar panels. And Monica showed this one. This was the first image that was screened to the world, where you could see Philae going down. But what the rest of you didn't see was the principal investigators in the control centre. And I mean, what a bunch of kids, you know. Very exciting times. There's the whole sequence. Monica's already shown you this. She hasn't shown you this though. These are the images 40 metres above the surface. That's what the lander would look like superimposed on that surface. So you can kind of see this was one of the best places we could go to in terms of being flat and free of rocks. But even so, not a brilliant place to try and land. And that was an image shortly after landing, when obviously it hadn't quite anchored onto the surface. So these were the measurements that we did at the different times. I'll skip through it. That is kind of how the Philae has ended up. This is a couple of science issues. So you can see this is why the drill couldn't reach the surface, because the thing isn't like this, it's stuck on its side. It's a good job it's stuck on its side, otherwise it would have skipped straight off the surface and probably gone back into space. And these are the results from our instrument. These were obtained actually when the instrument touched down, and what it did was it kicked up some dust, and the dust went into the instrument. So we did, and this dust will have come from about 20 centimetres, because the little dents in the surface of the comet that have been observed are thought to be about 20 centimetres deep. So we got dust from 20 centimetres depth into the instrument at the Agilkia landing site, so at the landing site that was selected. And that was something that we couldn't actually have hoped for, because that's exactly what we wanted, and we never had to use the drill for that. So what you do when you do that, you kind of try and fit it to your favourite comet molecules. It's very difficult, but I was kind of convinced that in actual fact it had some relationship to this polymer that was observed by in Comet Halley. You can see what these guys were getting, this kind of wobbly looking trace here. And so what I did was I put our spectra together. I've taken out water and CO2 from this. These are the major volatiles. And then fitted the Halley data on the top of it. And I think you could see that there is some kind of fit there. And not only that, we have a tremendously good resolution with the individual masses there. And this is the material. It's polyoxymethylene. It's a formaldehyde polymer. And the engineers might know it because it is an engineering material. It's used in all kinds of plastics. I mean, for me, I know it from guitar plectrums. That's what they're made out of. And it gives this very it depends how the molecule is actually terminated, but it gives this quite characteristic pattern of masses. And you can fit that to this, and you can actually see that there is some polyoxymethylene there. But there's definitely a whole load of other things, and this is all to still be interpreted. The interesting thing is the things that are missing. There's no benzene, so there are no aromatic rings. There is no black stuff. This is all white stuff. There's also no sulfur. So something else we might have been looking. We might have thought the black stuff was sulfurous. No, none of that. So we think we've got something far more primitive than the surface. We actually punched down into the more primitive layer. And there's some peaks there that we still haven't identified at all. These are or rather, we still haven't decided what we think they are. We know what the masses are, but we're not quite sure what they actually are. And anyone can have a go at interpreting this stuff. It's all publicly available. It's all on the Planetary Sciences Archive of ESA. And there's some things that we still haven't recognised. And polyoxymethylene was predicted by Chandra Wickramasinghe, if you know the name, in 1975 as an interstellar grain. So, in other words, what we're looking at in the comet here is stuff that the comet was made from. So this is stuff that predates the solar system. That's our current thinking. As Monica said, it got very active due to perihelion. But one thing she didn't show is this is what the dust environment looks like. And this is why the engineers are so damn scared about getting close to the nucleus. Some of these dust particles here, this is one that's come quite close, are 2 meters in size. So just so you get some scale of what's going on here. They're very low density, of course, but even so, they want to get far away from it. So we've gone right out to long distances during the main activity phase, and we're slowly now coming back in. And November the 7th, we will start another listening campaign, and we're all geared up, ready to go for some further measurements. I'll show you this one here. This is something else that scares the engineers. This is 3 images of the surface. See that thing there? That's a 50-meter boulder coming off. They're not happy, you know. And that just shows us where we are actually today. Okay.
Philae looks to be a great tool for exploring asteroids. How much does it mass and can you build more of?
Yeah, you could build as many as you like. And people always ask me, they say, well, of course, you built that a long time ago. What would you do differently if you did it now? I don't think I'd do anything different.
How much does it mass?
The mass is about 100 kilograms for the entire thing. And we still have all the drawings and so on. You could easily build another one off them. We try and make sure the harpoons work this time, you know.
Python Texans take the safeties off.
Yeah, I'd get the lawyers to have a look at it, you know, to see what they could do.
You said you had a plan possibly to write the philae or to change its orientation.
Yeah. Well, it's personally, I think it's probably moved since it actually finally came to rest, and it's part of the reason why I'm having some communication problems. But philae can rotate, so it can rotate independently of the legs, and the legs can go up and down. This is all part of, you know, how it was going to drill and so on. So we can actually command it to do all that kind of stuff. We've just been a bit nervous about doing that without having a stable link, because we can't then see what's happened to it. So we have done some blind commanding. So we have run our instruments blind, and all the data are presumably stored on the spacecraft, but we haven't been able to get a stable link to get the stuff back. It's quite frustrating. But we've still got a few weeks to go. We've got until maybe February next year, and the Rosetta's now getting close enough to establish the link.
So it sounds like the comet goes off a fair bit of acid, so it goes around the sun. Would that mass come back to it? Or is that mass gone forever? And it picks up more?
A lot of the mass stays in orbit, so the comet is going round. Some of these 2-meter grains are probably just staying in orbit with the comet.
Yeah.
And I don't know what kind of shooting stars you get down here, but on certain days of the year you get shooting stars like the Leonids and so on. And that's the day when you go through a cometary tail. I mean, that's why you see so many all at once, is you're going through the dust particles that are actually just kind of spread out in the orbit of the comet. So in principle, no, they don't go back to the comet. Some of them probably do. So it's a kind of one-way move for dust.
Wow, so it gets a fairly smaller every time.
Yeah, and they eventually die because you run out of stuff to degas, and that's why there's this grey area between what a comet is and an asteroid. There's something in between which is kind of half one and half another.
Okay, I think we have to keep moving. Some of us have to scoot out at the end of this, but I think the idea would be to